There is another approach by Fruscia based on Coleman's iterated integration, but my approach will be based on Deleuze's ideas, since I am interested in explicit formulas. So if one thinks about what are motives over Z, so there are no abelian varieties over Z with good reduction everywhere. So there are no curves with good reduction except the projective line, and projective line has cohomology Zn. So then one thinks about it's natural to think about what are the extensions of Zn, iterated extensions of Zn, which have good reduction everywhere. So Deleuze, I guess, thought about this example. So if you take, what's a picture that looks the same when you look at its reductions modulo different primes? So if you take the projective line and omit 0 and 1, then this looks the same modulo each prime. And if you're interested in the fundamental group, the problem is that you need to choose a base point. But once you choose a base point, then you want the base point, you want the picture to look the same with the base point. But then for this thing to look the same for each prime, this point has to have finite reduction at each prime. But this having finite reduction would mean that this has to be a unit in Z, and then it should not be congruent to 1 modulo any prime. Of course, the units in Z are plus and minus 1, and they both reduce to 1 modulo 2. So then one has to be careful when choosing a base point if one wants a picture that remains the same. So Deleuze thinks about choosing tangential base points at 0 and 1 such that on the tangent space this point corresponds to the vector 1 and this point corresponds to the vector minus 1. So then I'll say a few things about the Betti-Doran realization of this picture, and then this will be this will give usual multi-zeta, and the crystalline Doran comparison of this picture realization or comparison of the same picture will give p-adic multi-zeta. And then I'll talk about rather than this. So this can be viewed as Gm minus 1, and then I'll talk a little bit about Gm minus mth roots of unity, and then if P does not divide M, this is going to give cyclotomic p-adic multi-zeta. And then I'll talk about how to compute how to give a series representation. Up to depth 2. So about the Betti-Doran picture, so let's suppose that K is a field of characteristic 0 and X is a smooth and geometrically connected variety. So then one has this interesting category, modules with integrable connection. So on X over K, which have regular singularities at infinity. So regular singularity, whether some module with connection has regular singularities, could be checked by looking at curves. So so these are objects such that if you have any compactification of X with x bar minus x, a strict normal crossings divisor, then these objects can be extended. The vector bundle can be extended to the whole space such that the module has, the connection has log singularities at infinity. So an amazing theorem that starts this whole thing is the generalizations of Grothendieck's comparison theorem, which says that if k is equal to c, then the following holds. If you look at modules with integrable connection with regular singularities at infinity over x, and if you take local systems on the corresponding analytic space, so you take the underlying topological space with the complex topology, and then you look at locally constant sheaves of complex vector spaces. So there is a solution functor. So if you take E nabla here, then one can look at the horizontal sections, and that gives the locally constant sheaf of C vector spaces. So this is an equivalence of categories by Riemann-Hilbert correspondence of the. So in this picture, if one looks at the unipotent objects, in other words, if we look at modules with integrable connection, which has a filtration by subbundles with connection, such that the graded pieces are a trivial bundle with the trivial connection, then they form a subcategory. So modules with integrable connection, which are unipotent, of course, they correspond to the unipotent local systems here. So now, so what are local systems on X analytic? They are representations of the topological fundamental group after we choose a base point. So these are the unipotent representations of the topological fundamental group. So the unipotent representations of the topological fundamental group can be described completely algebraically. So let me try to say a few more words about this modules with integrable connection. So in our picture, we will be in the following setup. So there will be an important base point, which will only exist in the Dörrem realization. So this is generally called a Dörrem base point. It is essential. It's important that this base point will not. There's no analog of that in the other realizations. So this will exist under the following condition, which will be verified in our situations. So assume that X has a compactification X bar such that H1 X bar O X bar is equal to 0. So in this context, if we have an E nabla here, then so we can extend the vector bundle to the whole space such that this has regular singularities, but of course there are many ways of extending this. So in general, one can you can differ the eigenvalues of the matrix by sums of multiples, integer multiples of 2 pi I. But if you have a unipotent connection, there's a natural choice. Namely, if you want the residues at infinity to be 0, then there is a canonical extension. So if you have E nabla, then you can send it to E canonical nabla. So this is again a vector bundle with a connection with logarithmic singularities at infinity. And such that the residues at the missing points of the connection are nilpotent. This has the advantage that if you have an exact sequence of vector bundles with connection, and then of course you can forget the connection and get a map to E canonical. So then the important thing is that this functor takes exact sequences to exact sequences. And moreover, because of this condition, this bundle is always trivial. So under the assumption that under star, E canonical is trivial. Of course, once you know that E canonical is trivial, you know what it is exactly. E canonical is exactly its global sections times O x bar. This is over. Okay. So then, in the Doram case, if we have, so we have this category module, which is a Tanakian category, and so we have the following functor omega Doram to vector spaces over K, and this sends E nabla to global sections of the canonical extension. So omega Doram E nabla. So omega Doram is a fiber functor, and because of this property, because of 1, if I choose another base point, K rational base point, then of course I have another fiber functor omega x, which takes the vector bundle with connection to its fiber at x, and because of 1, there is a natural isomorphism between omega Doram. In particular, there is a natural isomorphism between two different fiber functors, because both of them are canonically isomorphic to omega Doram. Hence, there is a canonical path. So if I can denote the corresponding paths between x and y by p Doram xy, there is a canonical Doram path between these two. In other words, there is a canonical isomorphism between omega x and omega y for any x and y. Between and this is also valid if we, instead of x and y, if we use tangential base points. So now the comparison between these two categories give the following. So if we look at this usual picture, gm minus roots of unity, we take the tangential base points at 0 and 1, and so in the Betty case, there is a canonical path between these two base points, namely the one invariant by complex conjugation. Let me denote this path by gamma 0, 1. But then, so this is analytic continuation along this path. But then by Riemann-Hilbert, this is the same thing as P Durham T01 T10. But then in the Durham case, we can identify any fiber functor with the Durham fiber functor. So then we are looking at paths from Durham to Durham. So we are looking at automorphisms. So if I denote this thing by this, pi 1 Durham x, what I mean exactly is automorphisms of the fiber functor omega Durham. So pi 1 Durham can be described explicitly. So pi 1 Durham is easy to describe. So if one has a vector bundle with connection on Gm minus mu n, so let me extend it to, let me let K to be Q zeta, where zeta is an mth root of unity. So then this is a pro-unipotent group, and the universal enveloping algebra of its Lie algebra is just K, and then we have E0, E1 up to EM, where E0 corresponds to residue at 0, and EI corresponds to residue at zeta to the I. In other words, EM is the thing that corresponds to residue at 1. So then, if we just follow this thing, if we take this element and continue like this, we'll get an element in here which is group-like. So gamma 0, 1, the Betty path, gives an element inside this algebra. And then if we compute the coefficient, so if I have an element in some non-commutative formal power series, I'll denote the coefficient of an element with this notation. So in order to not, let me be careful. So if I look at the coefficient of this element, E0 to the sk minus 1, eik, dot, 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 E0 to the s1 minus 1, ei1, this coefficient is exactly equal to minus 1 to the k of this sum, n1 greater than 0, and k greater than 0, the other ones, zeta to the ik, and k minus 1 minus nk plus dot 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 minus I1 and 1 divided by and k to the sk, and 1 to the s1. And I guess I'm assuming that sk is greater than 1. So, sorry?
Not k.
Which one?
So,
Here?
no, the coefficient, this is a complex number, but this is a real number. This is not the element of k, this is a summation.
This is in k, right? Oh, sorry. Oh, you're right. You're absolutely right. Yeah, sorry. You're absolutely right. The correspondence is over C. You're right. I mean, this correspondence is over C as well.
But you also fix the roots of unity, right?
Yes, I fixed it. Yes, I fixed it once and for all. Exactly. So,
I have a question.
yes.
So I'm a little confused. So when you look at, you compare omega x with omega de Rham, do you need to extend scalars somewhere?
No, this is, as long as x is defined over k, the equality is defined over k as well. No, you don't need to extend the scalars. So the isomorphism is defined over the field that the point is defined. Okay. So now, this is exactly this is exactly so-called Euler-Kontsevich formula. So this thing could be expressed in terms of iterated integrals, and then this is the usual formula. So what is the crystal? So let me now talk about the crystalline analog of this whole picture. So now, crystalline de Rham comparison. So in this setup, R will be a complete DVR with residue field K, with residue field small k, and field of fractions big K. I don't know if I assume it everywhere, but let me say that it's perfect. I probably don't need this. So then, let me talk about the Betty. So the crystalline realization will replace the Betty one. So in some sense, the crystalline Frobenius could be thought of as the analog of complex conjugation. So rather than looking at local systems over C, we will look at the following thing. So let me first define convergent isocrystals. So let Y over K be a variety and assume for simplicity that there exists a P, a formal scheme over R, and then embedding of Y into the closed fiber. And moreover, assume that P over R is smooth in a neighborhood of the image of Y. So then, convergent isocrystal is a locally free sheaf of finite rank on the generic fiber so let me first say this. So there is the notion of a tube of Y in P. So these are the elements so the generic fiber of the formal scheme is a rigid analytic variety. So we have y in the closed fiber, and now we are looking at all the points in the generic fiber that reduce to the points inside y. And a convergent isocrystal on y, it's a bit strange when one first sees it for the first time. It's an object on the generic fiber of the formal scheme, which has, these are the points that reduce to this thing. So it's a locally, these are locally free sheaves of finite rank, together with an integrable connection plus some other important property. So in general, so if we recall Grothendieck's version of a connection, if we have a variety X and a connection on a vector bundle with connection on X can be viewed as an element as a vector bundle on X together with an isomorphism. So we have delta diagonal embedding into X cross X, and then we have its first infinitesimal neighborhood, and then we can pull back our vector bundle to this first infinitesimal neighborhood of the diagonal in two different ways. So a connection, in fact, is an isomorphism between the two different liftings of E into this one. In other words, a connection is a vector bundle on the variety together with information of local transport in the first infinitesimal neighborhood. But if that connection is integrable, then that parallel transport can be extended to the formal neighborhood of any point. In this case, the condition is that the connection not only can be extended to the formal neighborhood of a point, but it can be extended to the whole p-adic disk of radius 1 along each point. So in other words, a convergent isocrystal gives you information of how to do local transport in p-adic disks of radius 1. So let me not say it in detail, but let me write it like that. Plus, the connection converges in quotation marks in p-adic disks of radius 1. So this notion is not the right notion if y is not proper. So the right notion is that one has to assume convergence a little bit more. But then in our case, so those are called overconvergent isocrystals. But then in our case, they'll turn out to be the same as the logarithmic version of that. So let me say that. So now let's assume that P has the following further property. So now let's assume that P over R is proper, and then there is a divisor. So P over R is proper, and there exists a divisor inside. Well, I don't. Maybe I should just state it vaguely because I might not have time. So, so assume that if there exists y bar and the d inside here such that this is strict normal crossings divisor, and then assume that the whole picture can be lifted into R. So P over R, assume that is proper smooth, and then there is a divisor with strict normal crossings in P relative to R, such that this picture is obtained by reduction mod P. So, of course, this need not always occur, but it occurs in our picture, and actually the whole thing can be generalized. Then one can define a log version of this, and then this will be very similar to this one, except, so remember that we were looking at vector bundles with connection. So we have Y, and then we have its compactification. And so now we are looking at all things that reduce to points of Y bar. And then not only do we assume, okay, so let me not state it exactly, but these are the analogs of vector bundles with log singularities at infinity, analogs of E nabla, such that nabla has logarithmic singularities at infinity along D. So then there's a comparison with the Dorham version. So if we have now X, a variety over, let's say, R, proper smooth, variety. Again, there's a D in X, normal crossing, so on. Let me actually denote it with X bar, and then X will be, and let's let X to be X bar minus D, the generic fiber of this. Then there's an equivalence of categories with modules with integrable connection on the generic fibers, and isocrystals on the corresponding log version. So X bar log over K, again unipotent. So this is the first version of this was proved by Berthelot. In this version, it could, I think it's due to Shiho, although I'm not sure, so maybe I should try. So the important thing is that this part, the isocrystal part, has a Frobenius. So this is the most important thing. So then, through this isomorphism, there is a Frobenius on this one as well. So this will be the important thing. So, so now let me try to explain the situation. So, so now in our case, if I let X to be Gm minus mu m, or let this thing to be Xm, and I assume that P does not divide M. So then, let me lift everything to Qp zeta. So let K to be Qp zeta. So then, we have pi 1 Dorham X. And again, I have to choose a base point, T01. So, okay, let me say it like this. So I have the Dorham path from the T01 to T10, and then so I lifted everything to K, and then there's an action of Frobenius on this one, which is gotten through this analog of the Riemann-Hilbert. But then remember that there is an canonical Dorham path. So sometimes one is inclined to, rather than using this tangential base points, one is inclined to use the omega Durham instead of T01. But then omega Durham is not stable under the action of Frobenius, so it does not define a map. So one really has to choose genuine base points to be able to define. So there is omega Durham. Applying Frobenius, one gets F lower star omega Durham, which is again in here. And then one can identify, at this point, one can identify with the Durham with the usual tangential base points, so one gets an element in here. But then these are exactly sitting inside K E0, E1 up to EM. So then, if we, so then let's try to so let me denote this thing, let me give this thing a name. So let's let GM, or let me write it like this. Let me take a tangential base point at zeta I, and then apply it to here, and then let me call the resulting element, and let me put an I here, and an I here, and let me denote the corresponding element by GI. So,
okay, can you explain what you've written? You started off with omega in the torsa,
here,
and then in the next line you're in pi 1.
yes.
What does it refer to?
Yes, sorry. So actually, let me look at this case, because in the other case I have to be careful where F sends this thing to. So omega Durham is an element in here. F lower star applied to this one will give another element at the same groupoid. But then after that, I can identify, once I get the element in here, I can identify these base points with the omega Durham. So then I'll get a path from omega Durham to omega Durham, and that I denoted by pi 1 omega Durham. So I cannot start identifying it here, because then the Frobenius will not map from, will not define a morphism. But after I get an element, we can identify. So then, let me denote this thing. So then, so this gives an element in here. So then one can do similar things with the other. So this is the thing that corresponds to this path. So one can do similar things with the zeta I, but of course one has to be careful where F Frobenius sends this one to. So similarly, so this we called with denoted with G, which will be the same as GM. The one corresponding to this one, I'll denote it with GI. So then, the action of Frobenius on the whole fundamental group, pi 1 Durham, xn T01, can be described in terms of these elements. Such that F lower star on any, so F lower star on E0, since I'm choosing this tangential point, it is very easy to describe. The other ones are described as follows. F lower star on EI is P times, so let me be careful, P times G I have to correct this part, EI, GI. So since I have to replace I over here with I over P, or P times I, which I always get it wrong. So okay, it's I upper bar, where by I upper bar I mean the unique I between 1 and m that has the property that m divides I minus p times. So this is pi lower bar, I upper bar is the other one. So p times I upper bar minus I, and I lower bar and I upper bar between 1 and m. So then the question is, how can we compute these values? So unfortunately I can only compute it up to depth 2. But let me try to explain that. So the problem is that, so here's the problem. If I let un to be the whole P1 Cp minus the disks around roots of unity of radius 1, so in order to compute anything, I have to choose a lifting of Frobenius. In order to make a computation, choose a lifting of Frobenius. But the problem is that the Frobenius lift that we choose has to be a lift of the logarithmic object. So in other words, it has to, if I look at xn bar, which of course is nothing other than P1, the lifting has to behave well at infinity, which means that if I look at the divisor at infinity, then if I look at the pullback under the lift of the Frobenius should act as multiplication. So it will be ramified. So it should act like the way z goes z to the p acts at 0. So so the thing is that the lifting of Frobenius that is simple to compute is just z goes z to the p. But then this f does not behave well at roots of unity. So then f defines a good lifting of Frobenius only on un. Defines, and maybe I should use the word admissible lifting. Only on un. Of course, you can ask, why do you choose the lifting of? So, in case m is equal to 1, you could say, why don't you choose a good lifting of Frobenius that is okay on 0 and 1? But then the answers in that case that you get, even for zeta values, are extremely complicated. Even for zeta 3, you get a horrible expression. You don't get any of the standard expressions. So the good lifting of Frobenius is this one. But then the problem is that, the lifting of Frobenius that gives nice formulas is this one. But then the problem is that this one does not behave well at 1 and the roots of unity. But then the problem is we are interested in the path from 0 to 1. So it is not a good lifting at the point we are interested in. So then one has to do a trick. So the idea is the following. So if we look at so by using the Dorem path, we can trivialize the. So I can first fix a path. I can first fix a point 0, and then, in fact, I have to choose the tangential point at 0. But let me ignore that. Let me choose the base point 0, and let me look at the torsor of paths that start at 0. So it will be a torsor under the fundamental group at 0. Because of the Doran fiber functor, this torsor will be trivial everywhere. So let me denote this torsor by T Doran, and let me denote it by bar. So since this lifting is a good lifting on UM, this Frobenius will give me such a map. So the Frobenius will be horizontal with respect to the canonical connection. This Doran torsor will have a canonical connection just by functoriality, and then by definition the Frobenius will be horizontal. So then we'll have such a picture. And then we can take the derivative here. So this will be, after we identify everything with this, we'll have Li pi 1 Doran xm tensor omega 1. It might have log singularities at 0 to d pi 1 Doran xm tensor omega 1 and log 0. Here the map is nabla. Here it is F upper star nabla.
Why you have a 2 star, F star, upper star, lower star?
Which one?
So the
What's that?
Oh, sorry. Thanks a lot. Okay. And this is Li of F lower star. Okay. So then this gives a differential equation. So if I denote the image of the Doran path by under Frobenius by F, so this curly F is a good lifting of Frobenius. So if I look at where F lower star sends the Doran path between 2 points, omega Doran from 0 to Z, if I denote this thing by GFZ, where I will again think of this inside this big thing, its value here. So then we'll have this following equation. So derivative of GF is equal to this thing EI F upper star omega I, where omega I is d log z minus zeta I. If I is between 1 and n, it is d log z. Omega 0 is d log. So this is this thing times GF minus GF times PGI EI GI inverse GI omega I lower bar 0 I with the convention that 0 lower bar is 0. So the problem is that if you want to solve, we want to find GI using this equation, but then we don't know GF and we don't know the GI. So there are too many unknowns. So one has to do some trick. So the trick is the following. So I will use I characterize all rigid analytic functions on UN. So here's the proposition. So let F be a rigid analytic function on UN. And but for simplicity, let me assume that F0 is equal to 0. and let its formal power series expansion around 0 will be equal to an z to the n. So then, the strange thing is that if L is between 0 and Pm, P times M, and if this limit exists, limit as n goes to infinity of L q to the n, I didn't say what q was, q is the number of elements in the residue field of q zeta, qp zeta. If this limit exists, then it is equal to 0.
Excuse me. In a differential equation, the I start from 0, not from 1, right? What do you mean omega 0? Omega 0 means
D log z. Yeah, omega 0 is d log z.
Yeah.
Exactly. So this proposition is purely computational, but then it is very useful. So using these things first, inductively you get some power series expansions, and then check that by explicit computation you check that this limit exists, then by this argument you get that it is equal to 0, and then you continue like this. So the essential thing is that since f is a good lifting, its coefficients give you rigid analytic functions on un, so this proposition can be used. So the final thing is that if I, j, k are all different, then if you look at gi e0 to the s1, s minus 1 ej, e0 to the t minus 1 ek, then they are, so there is an explicit expression. It is too long to write. There is an explicit expression. This, let me write it this way. This is an explicit linear combination of terms of type limit as n goes to infinity of. So you again have exactly like normal power series, but then you have some conditions such as p does not divide n1, and in this case you have the condition that p divides n2, and then you have terms of type zeta to the a n1, b n2 divided by n1 to the k1, n2 to the k2. But then it turns out that these things are not convergent in general, so they have to be regularized in some way. But then I don't have time to explain that. And other terms which are of the following form: limit as n goes to infinity, 0 less than and sum of 0 less than n1 less than n2 less than p to the n, and then p does not divide n1, p divides n2 minus n1, and things of the form. This form. So again, as I said, this is I cannot at this point I cannot generalize it to depths higher than or equal to 2. So in case I, j, k's are the same, so there is a similar result if two of them are the same and one is different. But if all of them are the same, then the answer is completely different. But then the answer can be gotten using the usual p-adic multi-zeta values. I computed those values before, but the form of the expression is completely different if I, j, k are all the same. So I should also say that these p-adic multi-zeta values satisfy the shuffle relations, both of the shuffle relations. So the first shuffle relation is obvious for iterated integrals. The second shuffle relation is proved by Fruscio and Besser. And they also satisfy the Drinfeld-Ihara relations. I showed that they satisfy the 5-cycle relations. So, okay, let me stop at this point.
So, are there any questions?
So, here in summation, N1 is not divisible by P, but N2 is divisible by P.
Yes, yes. So one has to regularize the sum. It is.
So the numerator
Yes, it grows a lot.
a bit.
Yes, exactly.
This limit exists.
Yeah, after regularization. So this is regularization. I didn't. This is the important part. Yes.
So maybe the second term you have regularization.
This one, this one converges because both of them are not divisible by. This is not divisible by, and then this one is divisible. So this converges, and then this one has to be careful.
It's not clear the second term is converged because this is each term is invertible elements.
Sorry?
The unit, each term.
This one converges, yeah. Yeah. Yes.
What is the precise problem in going to higher depth?
I don't know. In the higher depth, I don't know.
What is the difficulty?
Oh, the difficulty is only computational. That I couldn't compute it. The same method should work for higher depth.
Combinatorial.
Yep.
When you say computational, can you put it on a computer? Or?
I'm not good with computers, so
But
maybe one can do it. Put it in a computer.
So you haven't done experiments with it?
No, because maybe a student can put it in a computer. It's fine.
This differential equation, there's no pole at the point 0, right?
It has a pole at 0. It has d log z.
So this collision, some collision might not be rigid analytic around 0.
DGF is rigid analytic at 0. Yes, but the canonical connection has a pole at 0. It is the canonical connection is d log. Let me write it like this: the canonical connection is omega I ei, where I ranges over 0 to f. But since GF is a good lifting of Frobenius around 0, it does not have a pole. So GF does not have
the point where you can apply these propositions, right?
Exactly. Yes, exactly. So if GF was not a good lifting at 0, then I would not be able to use.
Francis again.
So is it now known that these factorize through some suitable category of mixed state motives?
Sorry?
What's the status of knowing that these p-adic versions factor through categories of mixed state motives?
Who's mixed state motive? Okay. So one can also define for mixed state motives over some number field K. One can define in an artificial way p-adic periods. So one can first look at the p-adic étale realization and then use p-adic Hodge theory to get the Doran one and then get a number. So then these are exactly the p-adic periods of the mixed state motive. Yes.
Okay, if there's no further questions, let's thank the speaker again.